bits, right? Timer 0 is 8 bits, but at the moment we're just concerned with timer 1. And I told you 1 tick in timer 1 corresponds to 1024 if we set it that way. Okay? But timer 1 has 2 bytes, right? The lower byte and the higher byte. So the least significant bit of the higher byte, what is the value of that? 256, right? Does everyone understand this? No? Okay. So we have 16 bits, right? So you have 1, 2, 3, 4, 1, 2, 3, 4. This is the lower byte. Now I'm telling you what this value, what does that represent? What is this value? It's 256. Does everyone understand now why it is this 256? Or not? Because I think this is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 2 to the power of 8 is 256, I think. Yeah? So which means that 1 tick in the higher byte corresponds to so many CPU ticks. Everyone understand this bit? Yeah? Okay. So now the question is, channel 22, if 1 tick in the high byte corresponds to so many CPU ticks, how long is that? Given that the frequency is 16 millions clock ticks per second. So it means that if you have 16 times 10 to the power of 6 ticks, at least CPU ticks if you want, that corresponds to 1 second. Yeah? So I want you to calculate now how long does that take. I'm aware of some of you haven't done some mathematics for quite some time, especially those from BTech background. That's why I want to show this example here, because it will be very relevant for your lab today. So we have 40, we normally have about 43. Any more takers? The problem is I don't have a clue. Okay, now the field appears again. 91% says 8. Excellent. 7 9% says the other bit. Okay, for those 9%, let me do that on the board. So we have this number of ticks for 1 second. So for 1 tick, this corresponds to 1 divided by 16 to the power 10 to the power 6. Is that correct? And then we need so many. 2, 5, 6 times 10, 24 ticks is the same value, 2, 5, 6, which is the answer, which is this one divided by 16 million. I hope it makes sense for those who didn't get it well. Okay, so it's 16 milliseconds. So 1 tick in the 16 byte, especially in the high byte, corresponds to 16 milliseconds, roughly speaking. Now, let's look at this one, which is similar. Now, we want this one to overflow. Overflowing means it counts from 1 up until everyone is 1. So we want this number here to count up to 1, 2, 3, 4, 1, 2, 3, 4. And then if you want this again. But I would not count this because it's just 1 clock tick. It doesn't matter. So I want from here up to here. How long does it take for the high byte to overflow? So we know that one of them takes 16 milliseconds. So how many numbers do we have here? 2, 5, 6, right? I'm going to stop here because it's pretty obvious. Yeah. Which means that when the timer overflows, it corresponds to 4.2 seconds. So for example, in your coursework, for example, let me give you some hints about your coursework. Your coursework is about Morse code, right? And Morse code is made up of what? Dot and dash, right? Dot and dash. Let's say you want to test the length of your button. If, for example, you want to detect a dot, let's say you can set that to 200 milliseconds. That's your dot. If you want to detect a dash, then you should press a longer press, which is about 2 times this one, let's say 400 milliseconds. Okay, that's a dot and a dash. For one length Morse code, it is very easy, just this. But when it comes to 2 length Morse code, which means it can be a dot, a dash, dot, dot, dash, dash, dot, and a dash. I don't know which letters it represents. You need to differentiate between a dot and also the next symbol. Yeah? So that timing between these two, for example, can be that 4.2 seconds. That's a hint for your coursework. Okay. You will do that in the lab today, so you will. It will make more sense if you do the lab today. So we've been talking about interrupts, and we mentioned previously about enabling global interrupts, which was in the status register. So if you want to set that to 1, for example, this would be the syntax that you would be using. If you want to set that to 0, this is the AVR instruction that you will be using. Okay? But that's for all interrupts. That's for the global interrupts. Then, the timer 1 has its own interrupts. So you can enable the global, but if you don't enable specifically for the free interrupts, then they will not happen. If you don't set these to 1, then they will not happen. Okay? You can look it up in this document. Any questions? No? I did mention, for example, this one. Does anyone here remembers what it stands for? I did mention that in my last lecture. I didn't put that in the slide, but I did mention. TOIE. How many of you have got the instruction? Not the instructions, but this one. Especially those with the laptops. I can wait for 5 minutes. Sorry? Yes. It's to do with the interrupt or the overflow of the timer. So when the timer overflows, it creates an interrupt. Then you set it to 1 if you want this kind of interrupt to happen. Whereas these two are to do with the compare interrupts. So if the value of my timer matches the value in register B, for example, then it creates an interrupt. For this one, it is for register A. And this one is for the input capture interrupt. You need to enable. Okay, some useful AVRs. So I suppose by now you should know that this is clear. Okay, so all the values in R16 are 8 zeros. Whereas this one is the opposite. You set all the bits of your register to 1. So I had a question. One of your friends came down and asked me what this means, because he didn't understand. And that was a very, very small question. For those of you who do, for example, Java, what does that correspond to? Exactly. So when I do something like this, what I'm doing is I'm setting bit 5 to be 1. So I do 0, 1, 2, 3, 4, 5. And what is the other one? I'm setting bit 4 to be 1. And then the last bit is bit 3. I'm doing an OR operation. The final result is 1, 1, 1. That's what I'm going to do. That's the number I'm loading into register R16. Okay. You will see that in the lab today as well. This one, I'm not sure you will see that in the lab today, but this one is rotate through carry. And the carry bit is in which register? I did ask that question at the beginning of the lecture. One of you gave me the right answer. Yes. Sorry?
Status register.
Yes, it's status register. Okay? So that flag gets shifted to the right, whereas the least significant gets loaded into the carry bit. So what it has, it kinds of have an effect of division by 2, because this is the most significant, this is the least significant, and you're kind of shifting them. Whereas the opposite, this one is the opposite. I'm rotating through left. I have my carry bit here. I push it this way. Maybe it multiplies by 2. I'm not going to go through this one. Okay, it's pretty self-explanatory. But I want to, this one you have seen in lab 1, I think. But I want you to, this one is the most important, because you will have to know this to be able to understand the lab today. So what I'm doing is I'm comparing 2 registers. In this case it is R16 and R17. Okay? So let's say the value in R16 is the same as in R17. Which flag in my status register would be set or not set? Shall we stop here? 41. Let's stop here. Wow, it's very equally kind of divided. For this one, I'm not sure the global interrupt. Nothing to do with interrupt here. You're just comparing things. The 0 flag, I think, is the answer. Okay, let's see. Let's say I didn't know the answer, and I'm doing the lab today. I could look it up in the instruction set manual. It will tell me which flag is going to set. Okay. So when they're equal, the 0 flag is set. But now let's say they are not equal. So for example, in my next one, let's say this value is less than this one. Which of those flags okay, I want to ask someone with the laptop now. Let me see. Who wants to volunteer? Any one of those who have laptops? Especially those who are looking on the floor. No. Anyone would like to give me the answer? Because you have access to the instruction set. Come on. Marty? Let me have a look at whether you're looking at the right document first of all.
Yes, exactly.
If you look at this instruction set, it should tell you which flag it sets. I've already got 36 answers. Wow. I'm not in a rush because, you know, we have half an hour left. Daniel?
Yep.
Which flag?
I went with the negative.
Negative.
Yeah. So I figured what happened in the first one is CP takes the second register from the first register, so returns a 0 flag, because it will be 0 if they're the same. So this one, R17 is greater than R16, when it takes R17 away from R16, it will return negative.
Okay. Let's see the answers. 49% has gone on with your answer. Wow. Now, before I show you the answer, okay, let me log off here and
I guess
to show you how I would look it up, for example. Where are my lecture slides? No, it's not this one. So I'm looking for compare, right? Control L, probably will show me the whole thing. So if I look at this one, for example, can you see my pointer here? Yeah. Set. If the absolute value of this one is larger than this one, RD here is the one on the left, and RR is the one on the right. Do you want to change your answer now?
Yeah, go for it.
Okay. Did everybody understand that bit? Or not? No? Yes? Go through it again? Okay. So these are all my flags, right? N negative flag, Z 0 flag, and C carry flag. Yes? It's a bit small to see, but let me, if I zoom in, hopefully you will see. So I would set the carry flag, okay, if the value of this register is larger than RD. So RR here, if I look up, this one should be larger than this one. Then I would set this carry bit. Yes? Whereas in my previous quiz, I asked you what would be the value of which flag would be set if the result was 0. Yeah, equal, right? So how do I look is, for example, this RD minus this other register. So RD can be anything. It can be, for example, R1 minus R2. And if that result gives me a 0, Okay, that subtraction gives me a 0, and I look set if the result is 0. That's how I know that my 0 flag will be set. Okay? Hopefully we can come back. So now maybe you want to change the carry flag, right? But it's too late. Okay. How about the last one? So it's a bit different from the last one, right? If you look back, you see that sign over here? Is it already closed? Okay, tell me. We don't need the pudding. Tell me, which one do you think is the correct one? Huh? It's, some people are saying it's A, some people are saying it's B. Which one? Both. Yes. That's how you do. That's how you do the comparison, by checking your flag. Okay. So again, I want to point you to those two documents. One which has to do with the instruction set, and the other one which has to do with your hardware. Okay. So we have 25 minutes. You want to go on, and I kind of tell you how to do the coursework, at least for one part, or you are happy to break? Happy to break? No? Okay. I'm not going to tell you exactly the coursework, but at least go back. Okay, if you look at that marking scheme, okay, you have 10 marks for the overview of the implementation. What I want is at least the things that I'm looking for. Okay? What I want in this 10 marks is, for example, do me a flowchart. Everyone knows what is a flowchart here? No, you don't understand what is a flowchart. Okay, that's fine. So for those of you who do understand what is a flowchart, okay, if you go to, does this say? If you come to this one, can you draw me a flowchart? You have the loop here and the loop here. So once I'm at the back, I jump back to here. I want you to draw me a flowchart for this program. For those of you who know, can you do that now? I give you 5-10 minutes to do it. So when he runs, the roof is kind of looping, right? But here, you're checking the button.
Just waiting for answer. What do you mean? Hong Kong. Hong Kong what?
I'm going to ask one group to come at the front to draw me that particular chart.
Oh my God. So